Hello students, we're continuing with our study of momentum, and right now we're going to look at the law of conservation of momentum. Now it says that if I have a system, an isolated system, the total momentum of that system is going to stay constant. So it says that the total momentum initially is equal to the total momentum final. And this is going to be the case as long as it's isolated. It's always going to be true, even if crazy things happen. So for example, I could have two spaceships, spaceship 1, spaceship 2, and they're going to hit each other. Now before hitting each other, the total momentum, you get it by adding up the momentum 1 initial, that's for spaceship 1, and momentum 2 initial, that's for spaceship 2. And then after that, there's a tremendous smash up, explosion, whatever, and pieces go all over the place. But if you add up all the pieces, so piece 1, piece 2, piece 3, piece 4, piece 5, and so on, and F here means final. You add all of these momentums up, it's going to add up to the same amount that you had initially. So that's the law of conservation of momentum. So now we're going to be looking at a lot of examples here. But before we get into all of that, I want you to go to, basically I want you to stop this video, and then let me show you what I want you to watch. Hang on, let's bring it up. So here is, oops, there we go. Okay, so this is my Physics 2AG playlist. I hope you're linking to this playlist. And I need you to look at these, at least at first, these three demos. So now you can find them through my playlist, or you can find them by doing a search. For the first one, search on collisions demo, happy and sad balls. For the second one, search for collisions demo, 2 carts. And then for the third one, search on collisions demo, billiard balls. And I love this guy's ties. Oh, man, this guy's classy. He's from Utah State. All right, so I'm going to stop here. Okay, so you've watched the videos. And so now I think that this little example here will make sense. He had 2 cards, and let's see what this is saying. All of these problems are going to involve a before and an after. Before the collision, after the collision, or before the explosion and after the explosion. All right, so let's take a look at this problem here. It's saying we have 2 carts, and initially cart 1, which has mass 2 kilograms, is moving to the right with a velocity of 3 meters per second, and cart 2, which also has 2 kilograms, is not moving. It has 0 velocity. And then after the collision, cart 1 has a final velocity of 0, and cart 2 has a final velocity that, well, that's what we want to find out. All right, so this is our unknown. Now, the strategy is going to be to use conservation of momentum. In other words, the total momentum before is going to be the same as the total momentum afterwards. Here I kind of wrote it here. So total momentum initial is the same as the total momentum final. Okay, so let's find out what is the total momentum. So we take mass 1, which is 2 kilograms, times velocity 1 initial, which is given, right? 3 meters per second. So here it is, 3 meters per second. Mass 2, well, velocity 2 is 0. So here we got a 0. And, okay, so 2 times 3, 6. We have the total momentum of the system is 6 kilogram meters per second. What is the total momentum after the collision? Well, the law says it has to be the same. Yeah, it has to be the same. So, so that gives us a way to figure it out. Now, let's see here. I've got that whatever the number is, P total initial is our initial momentum, total momentum, but it's the same as the final momentum, whatever it is, it's going to be equal to the final momentum. Now look at, this is the final momentum. You know that because you see I wrote V1 final. So this is the mass 1 momentum after the collision. That's what the F says. This is the mass 2 momentum after the collision. Notice that in my setup of the problem, I said the final momentum of mass 1 is 0. That's why this is 0. And so we have that mass 2 times velocity 2 final is equal to our total momentum, which we figured out is 6. Okay, now remember, look, we have that momentum is equal to mass times velocity. If we want to solve for velocity, it's going to be V equals P over M. So we want the velocity 2 final. So it's going to be the total momentum. It's going to be, well, actually, I should have said it's momentum of mass 2 divided by its mass. It's the 6 kilograms, here's our 6 kilograms, divided by the mass 2, and we get the answer, 3 meters per second. So you're going to be asked to do a lot of problems like this, and I'm assigning you a packet of problems, and that they're on Canvas. But before we go any further, let's talk about elastic versus inelastic collisions. So in the first video that I had you watch, he had a happy ball and a sad ball. The happy ball was bouncy. And when it hit the ground, that collision with the ground was what we call an elastic collision. On the other hand, the other ball, the sad ball, it bounced, and it only bounced a little bit, right? It almost stuck to the ground, but that's maybe a slight exaggeration. But anyhow, we're going to call those a sticky collision. And in physics, sticky collisions are inelastic. Also in the video, you saw that he had 2 carts and they bounced, right? So one extreme was bouncy collision, and then he had 2 carts that stuck together because he had Velcro there. That's the other extreme. That's a sticky collision. Well, the difference between these is friction. When you have a sticky collision, like the sad ball, there's lots of internal friction in the rubber itself, and that friction converts mechanical energy to heat energy. When the Velcro sticks together like that, there's lots of friction happening all of a sudden, and once again, you have mechanical energy turning into heat energy. So when it comes to conservation laws, in both cases, the law of conservation of momentum works. The law of momentum conservation is like the most solid conservation law in physics. But we also want to use conservation of energy. We can use conservation of energy if it's a bouncy collision, an elastic collision, But if it's a sticky collision, then we can't. Okay? So if it's an elastic collision, we know that the potential energy plus the kinetic energy before is equal to the potential energy plus kinetic energy after. But if it's a sticky collision, we lose mechanical energy. So the potential energy plus kinetic energy afterwards is less than the beginning, right? The beginning energy, mechanical energy, is bigger than the final mechanical energy. All right. So now, what I want to do is get you started on the packet. All right. So this is something you download from Canvas. At the beginning, I have a lot of, I've got a few pages of solved problems. Now, these are all momentum related. Some of these are impulse problems. Some of these are conservation of momentum problems. There's a mix of problems here. And I want you to do all of these problems, okay? And you're going to upload them to Canvas. I've flagged some of these problems with some hints, like here. This is a conservation of momentum type problem. This is a bouncing and impulse type problem. Okay, so here are I start off with really simple questions, and then they gradually get a little bit more complicated. Number 9 here, this is a conservation of momentum problem. And okay, then we have, I'm going to go over this with you in a bit, but before I do that, I just want to show you one last thing. Way down at the end, there are the answers. So you can see whether or not you're getting the right answers. Later on, I'm going to make available full solutions, but for now, I want you to struggle a little bit, but this will help you. At least you got some answers there. All right. So now let's take a look at this example. So this is really similar to the one we were talking about before, but it doesn't hurt to have yet another example. Question: find the final velocity of the car on the right-hand side. Right? Now, what we could do here, call this one here mass 1. Now, mass 1 before, you see, it's always a before and after kind of thing. It has velocity 1. And if you wanted to, you could call it velocity 1 initial, although I didn't do that in the math down here. So the velocity 1 before the collision is 4 meters per second to the right, positive direction. And then over here, this is mass 2, and it has velocity 2, if you want, we could call it initial, and it's negative 4 meters per second. So they're coming together. So it looks very symmetric. However, mass 2 has 3 kilograms, whereas mass 1 has 1 kilogram. Okay, so the strategy is the same as in the previous example. We start by writing the total momentum. So the total momentum is the momentum of cart 1 plus the momentum of cart 2. Mass 1 times V1. Mass 2 times V2. We add those. We plug in the numbers. 1 kilogram, 4 meters per second for the first cart. Second cart, 3 kilograms, negative 4 meters per second. We do the arithmetic, and we come out with the total momentum of the system is negative 8 kilogram meters per second. Notice that it's negative. So Newton would say, the overall amount of motion here is the negative direction. It's going to the left. Yeah. So, okay, let's see now. Now, what we are doing is, you see, the total momentum is going to stay the same. It's still going to be -8 kilogram meters per second. But what we want to do is, since the thing we don't know entails cart number 2, let's see if we can find the momentum of cart 2. All right, so if I subtract the momentum of cart 1 from both sides of this, I get the momentum of cart 2 is equal to the total momentum, which hasn't changed, minus the momentum of cart 1. Now, the thing is, cart 1's momentum has definitely changed, right? So we're going to have to work on that. But let's plug in the total momentum, right? So we have the total is -8. And then we need the new momentum of cart 1. So it's minus, right? Minus. So minus the momentum of cart 1. So, okay, once again, the total minus. Now, the cart's still 1 kilogram, but it has a new velocity, right? Here's the new velocity. We could call that velocity to final. And that is what this is. This is velocity to final. Yeah, so it's changed. So now we have minus. So we have -8 plus 6.5, and we get the answer. The answer is -1.5. Oh, wait, no. Hang on. We don't yet have the answer. I'm sorry. We're getting warm. Let's scribble that out. We're almost there. To get that velocity, see, what we have is the momentum of cart 2, but we want to do V equals P over M, right? So we have velocity of cart 2 is the momentum of cart 2 divided by the mass of cart 2. Here is the thing we just figured out. The -1.5 goes here, divide by the mass, and now we get the answer. Okay, so here is the answer. This is the answer right here. And so it's negative 0.5 meters per second. And it's negative. So I want you to put an arrow to the left, right? This is V to final. It's going to the left. All right. I think this is a good place to stop.